Okay, class. In the last video lecture, we talked about how to draw Lewis dot structures of molecules. We're going to continue in a sense. We're going to talk about resonance forms and formal charges. Let's consider again the oxyanion carbonate, which we looked at a little bit in the last video lecture. It has a total number of valence electrons of 24. Now, I failed to mention, but you probably surmise, that in determining the valence electron number of 24, we have to add not only the valence electrons of the 1 carbon and 3 oxygens in carbonate, but also they add the 2 additional electrons that are the charge of the species that make it -2. So that's how you come up with 24. And then following the rules that we talked about, you put carbon in the middle, 3 oxygens around 3 different positions, distribute the 24 electrons. The additional electrons you put on the terminal oxygen atoms. You check for the octet rule. When you find that the octet rule is not satisfied for the central carbon, you resort to using 2 of the non-bonding electrons from one of the oxygens to form a second bond, a pi bond, giving rise to a structure shown as one of the following. And remember, when we looked at it before, I said just draw the double bond between the carbon and maybe the oxygen in the top position. But I also said that we would get back to that because that double bond really is a fleeting double bond that exists between the carbon and each of the 3 oxygens, or in other words, the position of the double bond is fleeting. It moves back and forth between the 3 different positions. This is what is called a resonance form of a molecule, or in this case, an anion. Resonance forms are forms of species in which the positions of the atoms do not change, or do not change appreciably, but the electrons and the bonds change position. In this case, the double bond goes between 3 different positions. Now, in reality, because the double bond is in all 3 places, I sometimes say in class, close your eyes, open your eyes, close your eyes, open your eyes, and you'll see the 3 different positions and that they're all equal in a sense. And sometimes we represent that as shown in the bottom right, where we put dots between the central carbon and each of the 3 atoms, to try to represent that each of the carbon-oxygen bonds is partially a single bond and partially a double bond. Now, a related concept is what is called formal charge, FC. And here we're going to talk about the trade-off between formal charge and electronegativity. And to explain this concept, let's consider cyanate. OCN minus 1. OCN minus 1 has a total number of valence electrons of 16. Carbon would be the least electronegative, so you'd put it in the middle and put oxygen and nitrogen on the 2 ends, or 2 sides of cyanate. You would distribute the electrons, again adding 1 more electron for the -1 total charge on the species. And when you do that, you would get this initial Lewis dot structure, where the 2 terminal atoms, oxygen and nitrogen, are dressed out with 6 non-bonded pairs of electrons for each. Now, a problem you would immediately notice is that the carbon, the central atom, does not satisfy the octet rule. In fact, it only thinks it has 4 electrons around it instead of 8. So this can't possibly be the final Lewis dot structure that we would arrive at. And in fact, we can come up with 3 different Lewis dot structures that are potentially viable by recruiting or using a non-bonded pair from either the oxygen or the nitrogen, 1 from each side, as shown in the leftmost structure, 2 of the non-bonded pairs from the oxygen being used to form a triple bond between the oxygen and the carbon, as shown in the middle, or 2 non-bonded pairs forming a triple bond between the carbon and the nitrogen, which is shown on the right side. So each of these is a potential resonance form of cyanate. And the question is, well, which one dominates? Which one is the best representation that accounts for the structure of cyanate? And it's important in this case because we are talking about single bonds and double bonds and triple bonds, and we'll learn in the next lecture that the properties of bonds depend upon whether or not they're single, double, or triple bonded. To decide between these 3 possible resonance forms, I ask you if you have brought to class, or if you have available with you, your lightsaber, and we'll show you how you can determine formal charges. Are you ready, Jedi? All right, using the lightsaber method of determining formal charges. Use the Force. So here are the three potential resonance forms that I had previously. Essentially, I asked you to take your lightsaber to slice between the bonds between each of the atoms. So we might slice between these bonds as shown. And then let the electrons, the two electrons that comprise each of those bonds, snap back towards the atom that they're closest to. Just had to get that in. Snap back, and as a result, you would wind up with something like this. If you look at the leftmost drawing, the oxygen would now have 6 electrons around it, the carbon 4, the nitrogen 6. The central drawing shows oxygen with 5, carbon with 4, nitrogen with 7, etc. And we can come to the third one in a second. Now, the reason for doing this is you ask the question, how many, for that particular structure, after we would slice those bonds and let the electrons snap back, how many electrons would that particular atom have? And so if we look at the leftmost species, the oxygen would have 6 electrons, carbon 4, the nitrogen 6. And compare that with the number of electrons that atom is, as I say, how many electrons was it born with? If it's just the element in the periodic table. Well, oxygen is born with 6 electrons, carbon with 4, nitrogen with 5. So you can see that the nitrogen in that first structure has gained an electron in this particular species. It has 6 instead of 5. If I look at the central species, prepared after slicing those bonds, you would see that the oxygen now has 5 electrons, but oxygen was born with 6. The carbon has 4, it was born with 4. The nitrogen has 7, but it was only born with 5. And likewise for the third species, the oxygen would have 7 electrons. It was born with 6, so it's gained an electron. The carbon would have 4, it was born with 4, and the nitrogen would have 5, it was born with 5. The key then is doing this addition or subtraction to see what the formal charge is of each atom in a resonance form. So if we go back to the leftmost resonance form, this analysis shows that the formal charge on the oxygen should be 0, the formal charge on the carbon should be 0, and the formal charge on the nitrogen should be -1. Now, by formal charge, we really mean, has it gained or lost an electron from what you would expect that element to have? In the second resonance form, oxygen has lost an electron, carbon has remained 0, no change, and nitrogen has gained 2 electrons, it's -2. The third resonance form, the oxygen has gained 1 electron, the carbon has stayed the same, and the nitrogen has stayed the same. So once we've determined the formal charge on each atom in the 3 possible resonance forms, we then ask the question, which is the most reasonable combination of formal charges for the elements in these species? And we do this analysis by comparing to the electronegativity scale, which we talked about last lecture. Remember what elements are more electronegative? Again, these are the same 3 species showing those formal charges. In the one to the left, the nitrogen has a -1 formal charge. The other 2 are neutral. In the middle one, oxygen is positively charged. Nitrogen has a -2 charge. And in the third species, oxygen has a -1 charge and the other 2 have no net charge. So which is most reasonable? Would you imagine, if you look at the one on the left, that if you had sort of a tug of war for electrons between nitrogen and oxygen, that nitrogen would pull the electrons away from oxygen so that the nitrogen would be negatively charged? No, that's not very likely because oxygen is more electronegative, has a higher affinity for electrons than does nitrogen. In the center one, a center resonance form, that's actually not very likely at all, because for this species, the oxygen would be positively charged. Oxygen doesn't like to be positively charged. It wants to be negatively charged. And the nitrogen, again, is even more extreme. It's -2. So that doesn't seem right. But look at the third resonance form. In this resonance form, the one to the right, the oxygen, the most electronegative of these three atoms, has won the tug of war for electrons. It is -1. The other two have no change. So this seems more reasonable. This is the type of analysis we're talking about. Determine the formal charges and then analyze them with respect to the electronegativity of the atoms to determine which of the possible resonance forms is likely to be the dominant form. In this case, for cyanate, we would say the species on the right would dominate. Okay, armed with this new analysis of formal charges, let's go back and look at boron trifluoride, which we did earlier. Total number of valence electrons is 24. We drew two possible resonance forms in a previous lecture, which are shown at the bottom. One in which the octet rule was not satisfied, that would be the species on the left, because the boron only has 6 electrons instead of 8. We then drew the species on the right by taking 2 electrons from one of the fluorines, bringing it down to form a double bond to satisfy the octet rule for boron. And at that time, armed only with our analysis that the octet rule is of importance, we probably favored the resonance form on the right. But now let's consider the formal charges. All right. Okay. We slice the bonds and let the electrons of each of the bonds snap back to the nearest atom. And when we do that and count the number of fluorines, and you need to be able to begin doing this in your head, count the number of atoms around the fluorine. Let's look at the one on the left. We would say the fluorine has 7 electrons. I need to shut off my lightsaber. If you look at the structure on the left, the fluorine has 7 electrons. Fluorine was born with 7 electrons. Boron has 3 electrons. Boron was born with 3 electrons. And so for the species on the left, each of the atoms has a 0 formal charge. Okay, neither good nor bad. But if you look at the species on the right, the resonance form on the right, after we sliced and diced and the electrons snap back to the nearest atom, 2 of the fluorines have 7 electrons, and of course fluorine was born with 7, so that's good. Boron has 4 electrons. It was born with 3, so boron has gained an electron and is -1. But look at the top of fluorine. It would now have 6 electrons. It should have 7. Fluorine has lost an electron in this tug of war with boron. Well, that certainly is not going to happen because fluorine is the most electronegative of the elements. For that reason, because the formal charges are just out of whack in the resonance forms to the right, we would reject that resonance form and we would favor the one on the left in terms of formal charges. So then it becomes a trade-off. The resonance form on the left does not satisfy the octet rule, but it has more reasonable formal charges. The one on the right satisfies the octet rule, but has out of whack formal charges. Well, in this particular case, the consideration of formal charge wins the argument because the structure on the left is the resonance form that exists for boron trifluoride. Now, actually, we have other evidence for this as well, which we will talk about in the next video lecture. So that's a good segue. We'll see you shortly.